Data is normally distributed if it is symmetric and bell-shaped. By bell-shaped, we mean that it starts low, slowly increases, and then decreases again. So that's bell-shaped, and it's normal if it's approximately symmetric about the middle, and that middle should occur about where the mean of the data is. Here are different normal distributions. So different normal distributions have different means and different standard deviations. Here is the normal distribution for heights of women. This is a sample of some number of women and a sample of some number of men and their heights. And we see that the mean for the women is, about 5'5" or about 5'4", and the mean for the men is about 70 inches. So these are different means, and we see that because it looks like the male curve is more spread out, that would tell us that that has a larger standard deviation than that of the women. Here is another normal distribution. This is for weights of cats, and they're saying that cats have a mean weight of 10.5 pounds and a standard deviation of 1.9 pounds. So here is our mean, and we've got a bell-shaped curve, symmetric about that mean, and we've got a standard deviation of 1.9 pounds. Here is an example of a distribution that is not a normal distribution. These 150 die rolls, this is not a normal distribution. We see that this doesn't fit a bell-shaped curve. And if you think about just rolling a six-sided die and what values you'd expect what we call approximately a uniform distribution, where the heights of each of the values are approximately the same. They all occur about the same amount of the time. So 1, 2, 3, 4, 5, 6. So rolling a 1, a 2, a 3, a 4, a 5, or a 6 are all equally likely. So they have approximately a uniform distribution. However, in real life, even though every event is equally likely, it might just so happen that, say, a 1 happens to occur in your sample much more often than a 2 happen to occur, and so on. But this is not a normal distribution because it is not symmetric and bell-shaped. Data from naturally occurring data sets is very often normally distributed. Some examples of data that tends to be normally distributed are measurements of an animal within the same species. So if you take, say, the length of a gecko or the weight of a bunny or whatever, if you look at those data values, they tend to be normally distributed. Exam scores, if you have an exam with a large set of people taking that exam, those tend to have a normal distribution, like SATs, GREs, the MCAS, IQ scores, and so on. Heights of plants within the same species, so if you talk about a certain kind of tree or at a certain age, or the height of a certain kind of bush or whatever, those will be a normal distribution. Some things that are kind of less natural also tend to have normal distributions. So if you think about some product and some measurement of a product, if there's many of them produced, say, a 12-ounce Coke can, they're intended to be 12 ounces, but it's not that they're all exactly 12 ounces. It might be that there's a normal distribution there with a very small standard deviation, or there almost certainly is a normal distribution there with a small standard deviation. And similarly, like the lifetime of a product, how long does this Prius battery last before it goes dead? That would also fall into a normal distribution. And we'll talk about why this is true later in the course. Basically, this can be explained by the central limit theorem, which we'll talk about later in the course. And we'll talk about normal distributions in general quite a bit when we talk about continuous distributions in a few weeks. Okay, so here's the empirical rule. It describes how data is spread out if data is approximately normally distributed. It doesn't have to be a perfect normal distribution, but if it looks pretty much like a normal distribution, then here are some approximations. About 68% of the data falls within one standard deviation of the mean. About 95% of the data falls within 2 standard deviations of the mean. And about 99.7, or almost all, of the data will fall within 3 standard deviations of the mean. So let's look back at that graph of weights of adult cats. Our mean was 10.5. There's our mean mu. And then our standard deviation is 1.9. So if we add 1.9 over, so this is the mean plus one standard deviation, or if we subtract one standard deviation off, the mean minus one standard deviation, then about 68% of the data values should be falling in that range. So 68% of the data values between the values 8.6 and 12.4 pounds. And so, yeah, we see that here is this large chunk of data values. About 68% of cats are going to weigh between 8.6 and 12.4 pounds. And similarly, if we add another standard deviation on, so this is the mean plus 2 standard deviations and the mean minus 2 standard deviations, in that range between 6.7 and 14.3 pounds, about 95% of the data should fall within there, 95%, between 6.7 and 14.3 pounds. And then, again, according to this data, if we go one more standard deviation out, so if we go out to this point, to the mean plus 3 standard deviations, the mean minus 3 standard deviations, then almost all of the data is within that range. We would have 99.7% of the data approximately within that range, or almost all of the data within that range. So we see that outside of that range, in these little tails, there's a very small amount of the data, but there are cats that are really heavy, that are 19 pounds or 20 pounds or whatever, and there are cats that are really small. There are cats that are, little teensy little 3-pound cats and so on. Okay, so let's look at an example. So weights of adult horses are normally distributed with a mean of 1,520 pounds and a standard deviation of 220 pounds. About what percent of horses weigh between 1,080 pounds and 1,960 pounds? And second, what is the range of values that contain the weights of about 68% of horses? So give each of these a try, and we'll talk about it in just a moment. For the first question about what percentage of horses weigh between 1,080 pounds and 1,960 pounds, we could look at the mean and look at the standard deviation, and we know that we're going to be talking about the mean plus or minus some number of standard deviations. So if you look at the mean minus 1 standard deviation, 1520 minus 220, that's 1,300. That's not small enough. So it's not just 2 standard deviations below, but if we look at the mean minus 2 standard deviations, 1520 minus 440, then we hit the value that we're looking at. So that's 1520 minus 2 times 220. 1520 minus 440 will give us this value, and the mean plus 2 standard deviations will give us this value, 1520 plus 440. 2 times the standard deviation will give us that value. So we know by the empirical rule that approximately 95% of the data values will fall within this range, because this is within 2 standard deviations of the mean. So here's our mean, our standard deviation, so mean plus the standard deviation, mean minus the standard deviation, and then we have to go one more out, mean plus 2 standard deviations and mean minus 2 standard deviations to get to the values 1080 and 1960. And so we know that about 95% of the data falls within 2 standard deviations of the mean. So for the next question, what range of values contains the weights of about 68% of horses? So 68%, we know that that's within one standard deviation of the mean. So that means one standard deviation on either side. The mean minus one standard deviation would be 1520 minus 220, which would give us 1300. And the mean plus one standard deviation would be 1520 plus 220, which would give us 1740. So that is the range between this value, 1300, and 1740. That should contain 68% of the weights of adult horses. And so what is the range of values? The range is the range from 1300 up to 1740, and that's in pounds. So we're going to talk about usual and unusual values, and the way that we interpret this idea is going to be based partly on the empirical rule. So determining whether a data value is unusual is clearly subjective. So one person might say something's unusual if it happens, less than 1% of the time. Another person might say if it happens less than 10% of the time, that's unusual to me. In this course, we are going to say that a data value is unusual if it is more than 2 standard deviations outside of the mean. For normally distributed data, this corresponds to data values such that having a value that extreme or more extreme occurs less than 5% of the time. So that is how we're going to define unusual in this course, being outside of 2 standard deviations of the mean. So as an example, suppose that the lifetimes of Duracell 9-volt batteries are normally distributed with a mean of 15 hours of use and a standard deviation of 2 hours of use. So if a 9-volt Duracell battery dies after 11.5 hours, is this unusual? Was this an unusually low amount of time for that battery to last? And if a 9-volt battery dies after 19.5 hours of use, is this unusual? So give that standard of being unusual and try that out. We'll just talk about it in a second. So pause and we'll talk about it in a moment. Okay, so in deciding whether it's unusual, we know it's unusual if it is less than the mean minus 2 standard deviations or greater than the mean plus 2 standard deviations. This is a value that's less than the mean. So what is the mean minus 2 standard deviations? That would be, in this case, 15 hours minus 2 times 2 hours. That would be 15 minus 4 would be 11. So it lasts an unusually short amount of time if it lasts less than 11 hours. So our answer here would be no, and it is no because it was within 2 standard deviations of the mean. So 11.5 hours is within 2 standard deviations of the mean. For our next question, if it dies after 19.5 hours of use, is that unusual? Well, this is on the high end, so let's look at the mean plus 2 standard deviations. That's 15 hours plus 2 times 2, that's 19 hours. That would be the mean plus 2 standard deviations. So this is greater than 2 standard deviations above the mean. And so, yes, this is unusually long because it is more than 2 standard deviations above the mean. The empirical rule also gives us some insight into the range rule of thumb and where it comes from, and perhaps even a better range rule of thumb. So we know that one thing that the empirical rule says is that for normally distributed data, about 95% falls within 2 standard deviations of the mean. So if we think about breaking up that range, so here's our mean, here's 1 standard deviation below, and 1 standard deviation above. And here's 1 standard deviation, or 2 standard deviations below. And now 2 standard deviations above. And now we can break that up. So this is 1, 2, 3, 4 chunks. And that contains 95% of the data. So, okay, that tells us that if we take that range and we divide by 4, so if we have the largest usual value minus the smallest usual value and divide that by 4, that is approximately 1 standard deviation. Because this is 1 standard deviation, this is 2 standard deviation, this is another standard deviation, and this is another standard deviation. So each of those chunks is 1 standard deviation long, and so if we break that entire range up into chunks, each of the same size, 4 of them, then that is approximately the value of 1 standard deviation. So the original range rule of thumb was it's the maximum value minus the minimum value, divide that by 4, the range divided by 4. Here this is a slight change. Instead of taking the absolute maximum value and the absolute minimum value, you say, okay, I'm going to throw out the outliers, or I'm going to throw out the things that happen less than 5% of the time, and I'm going to take the largest usual value minus the smallest usual value, divide that range by 4, and that is approximately the size of 1 standard deviation. So with the range rule of thumb, you can really use either of these. You can continue using range divided by 4 for the range rule of thumb, but this is usually a slightly better estimate of the standard deviation. The largest usual value minus the smallest usual value divided by 4. Now, if you don't know anything about how the data is distributed, there's still a theorem called Chebysev's theorem that will tell us how much of the data must fall within a certain number of standard deviations of the mean. So this can be proven mathematically. This is a guarantee, but the proof is based on some like Calc 3 and 4 understanding. Whereas the empirical rule is an approximation. So in the empirical rule, we're talking about data that's approximately normally distributed, and about 68% of the data will fall within 1 standard deviation, etc. Here, this is a guarantee that at least this amount of the data must fall within a certain number of standard deviations of the mean. So Chebysev's theorem says that for any set of data, and for k greater than 1, at least 1 minus 1 over k squared of the data falls within k standard deviations of the mean. So here, first of all, at least 75% of the data falls within 2 standard deviations of the mean. Using Chebyshev's theorem to figure that out, if we looked at k equal to 2, then we have 1 minus 1 over k squared. That's 1 minus 1 over 2 squared. That's 1 minus 1/4, or 3/4. And we know that 3/4 is equal to 75%. So 75% of the data must fall within 2 standard deviations of the mean. And if we look at within 3 standard deviations of the mean, then k is equal to 3. And so 1 minus 1 over 3 squared, or 1 minus 1/9, which is 8/9 of the data, must fall within 3 standard deviations of the mean. And 8/9 is approximately 89%. So notice that these are both kind of less impressive values than were for the empirical rule. The empirical rule says that if the data is normally distributed, at least 95% of the data falls within 2 standard deviations. and approximately 95%, and approximately 99.7% falls within 3 standard deviations. So there is, a stronger result if we're talking about normal distributions as opposed to a distribution that we don't know anything about, which of course makes sense.